In today's lesson, we're going to be learning a new technique that's called factoring by completing the square. Now, while this is still technically considered a factoring technique, most of its utilization comes later. That's what we're going to go into in the next chapter for solving quadratics, but it still allows us to do a relatively unique feature that is very useful compared to the content we've been dealing with in the previous chapter about graphing. So the first thing I want us to recall is that these equations I have right here are quadratic functions that we know how to graph just by simply looking at the equation. So for example, the first equation, y equals a quantity of x plus 1 quantity squared minus 7. In the last chapter, we knew that was shifted left 1 and down 7, which taught us to start right here. And then because there's no vertical stretch compression factor, we would just follow the pattern right 1 up 1, right 2 up 1, 2, 3, 4, right 3 up 9. We could duplicate these coordinates off to the side. And then from there, we could graph our function. Same thing with problem number 2, a little more complicated. It looks more complex, but it's still the same process because we have y equals negative 1/2 times the quantity of x minus 4 quantity squared plus 5. I know the x minus 4 means I'm going to be shifted right 4. I know the plus 5 at the very end means I'm going to go up 5. So right 1, 2, 3, 4, up 1, 2, 3, 4, 5, which takes me to right here. And now normally I go right 1 up 1, right 2 up 4, right 3 up 9, right 4 up 16, write a number, up that number squared. But we're going to take all those heights, multiply them by negative 1/2. The negative will flip us vertically. The 1/2 is going to compress all those heights that I just got done saying in half. So we are going to go right 1 down a half, right 2 down 2, right 3 down 4.5. And I could just duplicate those coordinates here. And then this is my parabola. So the key takeaway that I want you to have is that when a quadratic is written in this form, in this graphing form, this vertex form, it's really easy to graph. You just find the vertex and then plot the pattern. The issue is this entire chapter, for the most part, we've been dealing with a lot of quadratics, and they've all been in standard form, ax squared plus bx plus c. We've yet to see a vertex form equation emerge. And that's because in order to get vertex form, you kind of have to bring it into existence. You need a technique that allows you to go from standard form into vertex form. And that's what the technique we're going to do today is. The technique is called completing the square. So here I have a generic quadratic function, x squared minus 8x plus 10. And I'm going to complete the square so that I can get that equation into vertex form, like the red and blue functions I had on the previous slide. So how do we do this? Well, the first thing I like to do is I kind of like just to rewrite the equation, but I like leaving a little bit of a gap in between the negative 8x and the positive 10, and I'm going to put the 10 off to the side right here. We're going to hold on to that 10. We're going to deal with it later. We're going to put a pin in it. We're not going to really act like it exists very much, and we're just going to focus on the x squared and the minus 8. And what we're going to do is kind of a factoring technique, and we're going to use an area model, but this area model is going to be different. It's going to have two main differences between it and the other area models we've done already. The first and most prevalent one is that the area model is missing the bottom right portion. So it's missing a piece. The second thing is that I am going to, and you'll see why in a minute, I'm going to arbitrarily restrict this area model, and I'm going to say it has to be a square. So what does that mean? Well, I mean, the difference between a square and a rectangle is a rectangle, the length and the width can be pretty much any measure. But for a square, the length and the width have to be the same measurement. So if this is x plus 3, this is x plus 3. If this was x minus 11, this is x minus 11. If this was 3x plus 1, this would be 3x plus 1. So whatever the length is, the width must also be the same. And by having that restriction, is actually going to turn the factoring technique of completing the square into something a little bit more approachable, a little bit easier to handle. All right, so remember, we are only focusing on the x squared and the minus 8x. We are ignoring the 10 for the time being. So the x squared goes in the top left box. Now, in the two diagonal boxes, I know that those two combine together to get negative 8x. And here's the thing that makes this technique kind of nice. Because this is a square now, I also know that what is in these two boxes has to be the same measurement. So it has to be something like a 7x and a 7x, or a negative 2x and a negative 2x. Otherwise, it wouldn't make a square. So if I know that these two have to be the same thing, and I know they have to combine together to get a negative 8x, then each of these boxes, since they're the same thing, have to be each half of this term. Half of negative 8x is negative 4x. Because negative 4x and negative 4x combine to get negative 8x, and because they're both the same, now I have a square. And that square's measurements are x minus 4 times x minus 4. And now we get to the part that gives this technique its name. This technique is called completing the square because we have a missing piece of a square and we need to complete it. Well, negative 4 times negative 4 is going to give us our missing piece, which is positive 16. All right, awesome. We did this area model. What the heck is this all for? Well, I'd hope you agree that if I put the positive 16 right here, then x squared minus 8x plus 16, if I was just to factor that, again, remember, we're ignoring the 10 for right now. If I was to factor this, if I gave you that as a problem to factor, we would get this area model, and the answer would be x minus 4 times x minus 4. And x minus 4 times x minus 4 is just x minus 4 quantity squared. So if I had these three pieces, it would turn into this. Problem is, I can't just take a 16 and throw it into the equation. And I can't just ignore a part of it. I mean, that's just dealing with a different problem. That's me saying, here's the problem I have. I don't like it, so I'm going to replace it with one I'd like. So we're going to have to be a little crafty. What I'm going to do is I'm going to add the 16 here so that these three pieces factor into this perfect square. But if I add 16 into the equation, I've just added 16 units into an equation that didn't have the 16 units. To keep the balance, I'm going to have to also subtract 16 at the same time. And now we're going to deal with that plus 10 and the negative 16, because those things combine together to get me negative 6, and that's the value that goes on the outside. And now notice, I just rewrote the equation in vertex form. This is now the graphing form that we have been searching for. This quadratic, x squared minus 8x plus 10, if you were to graph it on a graphing calculator or Desmos, it would be a parabola that is shifted right 4 and down 6. This technique allows us to transition from standard form quadratics into vertex form quadratics. So let's do a couple more examples. Problem number 1, I have x squared plus 6x minus 1. All right, I'm going to rewrite it as x squared plus 6x, leave a little blank for the number I'm eventually going to write there. Then I'm going to put the minus 1. I'm going to draw the area model with the bottom right portion missing. The x squared goes in the top left box. I know that these two boxes have to combine together to get the positive 6x. Since this is a square, I know they're each going to be half of that value, so it's going to be positive 3x and positive 3x, which means the numbers on the outside are x plus 3 and x plus 3. Now that I know the outside values of my area model, I can figure out the missing piece. Positive 3 times positive 3 is equal to positive 9. That's the piece I'm missing. I'm going to put the positive 9 right here, but I can't just add 9 into an equation without also subtracting 9. These first three pieces, the x squared plus 6x plus 9, factor into x plus 3 times x plus 3, which is simply the quantity of x plus 3 quantity squared. And then the remaining two pieces on the outside, the negative 1 and the negative 9, are going to combine together to get me a negative 10. And here I have my answer. I have transformed the x squared plus 6x minus 1 standard form quadratic equation into vertex form, the quantity of x plus 3 quantity squared minus 10. That's a parabola that shifted left 3 and down 10. Next, we're doing problem number 2. While problem number 2 looks a little innocuous, it looks a little bit, simplistic, just like problem number 1. There is an issue with it that is going to make this problem much more difficult. So let's hop into it, shall we? We're going to have x squared minus 5x, going to leave it blank, and then put the plus 3. I'm going to draw my area model with the bottom right portion missing. You might begin to start seeing where this issue is going to show up. I have the x squared in the top left box, and here's where we come to our little conundrum, because these two boxes have to combine to get the negative 5x, and they each need to be half of the negative 5x. Negative 5 cannot evenly be cut in half. That's because, unlike problem 1, where the middle term, the linear term, was even at a plus 6x, and here the linear term is odd, it's a 5. When the linear term, the middle term, is an odd number, that means one of two things. Either you're going to deal with fractions or you're going to deal with decimals. I like fractions, so I'm going to write this as negative 5 over 2x and negative 5 over 2x. Again, I took that negative 5x, cut it in half to get negative 5 over 2. Because those are negative 5 over 2's and the top left is x squared, I know this is going to be x and x. Negative 5 over 2 and negative 5 over 2. So the piece that we are missing is going to be negative 5 over 2 times negative 5 over 2. A negative times a negative is positive. The way we multiply fractions is top times top. 5 times 5 is 25. And bottom times bottom. 2 times 2 is 4. So that's the piece we're missing. That's the piece that's going to go right there. Plus 25 over 4. But we also have to subtract the same value, 25 over 4. So if I was asked to factor x squared minus 5x plus 25 over 4, it would turn into x minus 5 over 2 times x minus 5 over 2, which would leave us with the quantity of x minus 5 over 2 quantity squared. The tricky bit is figuring out what does these two values combine together to make. Well, first I recognize that 3 is the same thing as 3 over 1. And this is going to still be negative 25 over 4. I cannot combine these two as they are currently written because the denominators are different values. The only way we can add and subtract fractions is if the denominators are the same values. So I need this to turn into a 4. The way I'm going to do that is I'm going to multiply the 3 over 1 by 4 over 4. We can get away with doing that because 4 over 4 is the number 1. You can always multiply something by the number 1 and not change its value, just the way that it appears. So the 3 over 1 is going to turn into 3 times 4 is 12, 1 times 4 is 4, minus the 25 over 4. And now that they have the same denominator, I can combine them by simply combining the numerators. Positive 12 minus 25 is going to be equal to negative 13 all over 4. And that would be our final answer. Of course, if you wanted to use decimals for these two values, you could get a 2.5 to be right here. And if you wanted to use decimals here and also in the work, that would also be fine. And that would give you a 3.25 if I'm doing my calculations in my head correctly. And this is how we complete the square to go from standard form equations into vertex form.